So good afternoon, everybody. Thanks for coming to my talk. Today I will do an introduction to circom-mpz. So that is about two-party computation. So I promise you that this talk is only about simple things, right? So we actually need to take a break after Jordy's talk at all. First, I would like to start with ETHTaipei to MPC. So imagine you have this problem between like you, 5 years old, and also your friend, 5 years old, right? So you are Alice and your friend is Bob. So after the new year, both you have received some red envelopes, right, with some amount of money. And then because like you are 5 years old, you have this childish competition between you and your friend. And you started to wonder that between you and your friend, who has more money from the red envelope, right? But the problem is you don't want the other to know your amount because, like, you know, it may be the case that you know, it's like money is some sensitive thing even for 5 years old. A solution could be you go to ask a trusted auntie, right? So you have this honest auntie that is available to you in the house. And then you say, okay, so my auntie is honest, she's an adult, she's going to keep the promise, right? And then you reveal your amount to this honest auntie. And also your friend also trusts your auntie and also tell this amount. And then because the honest auntie has already like know both the amount, right? So she can actually do the comparison herself in her head. And then say that, okay, I'm sorry, but your friend has more money than you. And she's going to keep the promise, right? Because she's honest and, you know, like, no, your friend doesn't know your amount and also you don't know your friend's amount. It's fair. But, you know, like, life is not that ideal. Imagine you don't have such a trusted auntie. What do you do? So I can tell you that you can replace this trusted auntie with the MPC auntie that is made available to you through some cryptographic primitives. So it's called MPC, right? So this actually gives the very much the same result. So you can tell this MPC auntie your amount, your friend does the same, and then this MPC auntie behave exactly as the trusted auntie. So this MPC auntie will only output the comparison result without telling the other your private amount. So this is what MPC is about, right? But maybe we can, you know, like grow up a little bit and then actually understand more about this MPC. So what is MPC actually? You can think of MPC as this box right here. So MPC stands for Secure Multi-Party Computation. So it is like the abbreviation of this M, P, and C, so multi-party and computation. But the actual name is Secure Multi-Party Computation. So we may all wonder why, you know, like there is no secure in the abbreviation, right? You might think of like, why not SMC, why not SMPC, but just MPC? Because like, what is the point of doing MPC if it is not secure? So secure should be implied when you do MPC, right? So that is the first property that we want. So you have this box of MPC that does some function f that Alice and Bob can use to input their private input, XA and XB. And this box will output the y, that is the function f computed on XA and XB. The three properties that we want out of this box is that, first of all, privacy. So we want to make sure that only Alice will know XA and Bob will know XB. The second property is called independence of inputs. So because like we may have this asynchrony in inputting the private inputs, right? So XA and XB, they may be put in the box at different point of time. So what if XA is input first and then XB can be dependent in some way? So you can imagine the scenario where you have like salary negotiation or, I mean, this infamous best friend or love, you know, like computation. So you want this independence of inputs to assure some fairness to the computation, right? And then finally, like also very, very important, you want correctness, that this output is indeed the commutation of the function f on the private input xa and xb. So MPC is as simple as this. You know, just replace some trusted thing with something that is cryptographic. So we have like ZK before, right? So what is MPC in the landscape of the privacy tool? Like what is MPC versus ZKP? So you can think about ZKP. So ZKP allows the prover to convince the verifier that an instant X is true, provided that the prover knows a witness W that testify the correctness of the instance. So basically you're checking this relation R between the X and the W, and you want to ensure that it is one. Now thinking of the term of MPC, you just like have this check put in this box, right? So ZKP, you can think of it as an application-specific MPC, but only the prover has some secret. That is W here, right? The verifier has no secret. So MPC that implements ZKP is a box that allows the prover to input some secret witness W that testify the instance. That is like X or X prime. And then the output is just a binary bit. But because like ZKP is an MPC that does only one purpose, it can be like very efficient because you can optimize like the computation based on the function, right? So ZKP is an efficient application-specific MPC that just does this thing. Okay, so like now thinking about application, you have application, you have ZK, then it becomes ZK app that allows you to do some like verifiable application, right? Like ZK rollup, ZK EVM, ZK VM. Now if an application, you add ZK, so that is like you have ZK app that is like private app that is also verifiable. But you can see that it allows you to have like only the privacy for the prover. The verifier has no privacy. Like example application, ZK ID, like semaphore or some other ZK ID protocol. So you can have private ID from the prover. ZK-ML, unfortunately, you can only have either the model or the sample that is secret. You cannot have both. So what if you combine app with MPC? So application, when you try to implement it with MPC, you can actually have like private parties inputs from more than one. This is by definition. So you can imagine PPML, that is an upgrade of ZKML. So you have both model and sample be private. And there are also other like applications has been considered before, like by cryptographers or some other company, private auction, private voting, or dark pools. Okay, so something that is like a little bit further ahead is FHE. And what is MPC versus FHE? So FHE stands for fully homomorphic encryption. It allows you to do computation on ciphertext. So you encrypt some values, and then you can actually do addition and multiplication on these values, right? Just by doing some operations on the ciphertext. It is a very, very powerful tool. It can be used to build MPC, but right now it is sort of like expensive. So it's really up to you. Okay, so I'm going to do a little bit of introduction to this Gabo circuit. So Gabo circuit is a technique that you can use to implement MPC. A Gabo circuit is particularly suitable for 2PC, like two-party computation, just you and your friend. So when you think about like MPC, right, it is going to be like this. But what we really care about is MPC that is programmable. So this is called generic MPC. This part where you have Alice and Bob, they have like some secret values. And this output Y is the same as before. But generic MPC allows you to input like this public circuit. For example, what I'm describing here in the slide is a computation of an inner product between like two arrays of 3 elements from Alice and Bob. So we want to compute the inner product of these 2 vectors without Alice knowing Bob's vector or Bob knowing Alice's vector, right? So we have got to describe this public circuit in some way. So, well, I mean, the name Gabo circuit coming from, circuit. So you can imagine like here, you do some multiplication for each of the array elements, and then here you do an addition, here you do another addition, and then you can get the result, right? So here is like 32 bits multiplication. Here is like 32 bits other circuit. So like we can describe roughly how Gabo circuit works. So in Gabo circuit, you have 2 parties, right? There is the one that is called the gabler. There is the one that is called the evaluator. This can be Alice, this can be Bob, or, well, they can switch role. We don't need to care about that. It's just that the algorithm they run are different. So the gabler is the one who will read the circuit description, try to encrypt it, and send along its private input in some encrypted way to the evaluator, right? So because this circuit is encrypted, the evaluator has to be able to decrypt it in some way using some decryption keys, right? So it can use like some mathematics here that try to obtain the decryption keys based on its private input here. And then it can decrypt the circuit and get the result. So what is nice about this Gabo circuit is that it has constant route of interaction. So imagine if you here are doing some computation with someone that is in America, it is not a problem for Gabo circuit because you just need to do this interaction once. And then you don't have to do this round trip a lot of time. But of course, there is the trade-off for high communication costs. There are other techniques that allow you to do less communication, but it requires higher route communication, higher number of route communication. So, well, it depends on the situation that you would want to use this technique or the other one. But like, it doesn't matter, right? Because, so believe me, I have done some due diligence, right? I would like to really explain to you the technical details behind this Gabo circuit. I've done this a couple of times, but like at the end, I realized that you don't really need it. I mean, if you really want to understand it, you can go here. So we have like some write-up for Gabo circuit. But, you know, like it is, because I've promised simplicity in my talk today. So let's skip all of these. You don't really need to understand it to start using MPC because you can use MPC. So this is a library initiated by the TLS Notary team. And at the MPC team, we have done some more work to make it have more features. So let's forget about Gabo circuit because all we need is actually focus on like how to write a circuit, right? How to describe this circuit here. It is what's important to us as the user of the technique. So you can use MPC. There are several hard ways. So you can try to use this circuit trace. So MPC circuits or some MPC circuits macros. To describe the circuit, it's going to look like this, right? So you describe like bit by bit, or even in the form of 32 bits computation. But still, like it takes you a lot of brain cells to be able to do this. Another way, which will not take your brain cell, because you will not able to do it at all. This is like the legacy of the cryptographic development in the past, right? There is this thing called the Bristol Fusion circuit that is like highly optimized description of circuits like AES or SHA. But you don't have circuits beyond those. Imagine you want something like, well, gadget, you may have it. Like some new Boolean arithmetic, some new Boolean circuit that comes like today, and you want to use it. Maybe there is no Bristol format for you to use, or it is not highly optimized as those that is before, right? So maybe just forget about this thing as well. A little bit easier, we make the description of the circuit in the arithmetic form, so you don't have to think about Boolean circuit. So it is called BMR16. You can do direct. For example, here you can do multiplication between A and B, and you can also do comparison. So it's like these guys are gadgets that allows you to build circuit easier. Still, I call this the hard way. What if I tell you there are more easier way that you can do? So you can actually write circuit in circom and run it with MPC. This is like some, we have like this circom to arithmetic circuit. It's an interpreter from circom that is very, very familiar with ZK devs these days. Also Arian and like some other PSE folks before, they talk about circom, right? That is like how easy it is to use. You have like tool chain audits like ready for it. So here, this is another part of the tool chain, let's say. You can write circom program and then you get some MPC circuit out of it. So how it works, like you have some circom programs. Some part of the circom lib is also working right now with our interpreter. You go through this interpreter and then it gives you a circuit JSON that is like an arithmetic circuit. And then you can write a loader here in MPC. And then just execute a circuit with some inputs from a coupler and evaluator. And then you get the output. So as simple as it is, you just need to write program in circom. Now, let's make an example, right? So privacy preserving machine learning with circom-mpz. So you can have some machine learning circuit in circom, do the same as before. Here, the loader, you read the weights and the samples. It gives you the inference result based on the circuit that you described before. So like one question maybe, how do we get these circom program for machine learning, right? Turns out there are abundant of them. You have this circom-ML that is from the Modulus lab. They did some machine learning circom for fully connected layers and a simple ReLU. There is also circom-lib-ML that is done by Kathy when she was with the PSE. There is also Keras to circom, also done by Kathy. And if you don't like Keras, you may use a tool to convert some Onyx model to Keras, and then you can use this. And then the rest of the tool chain is just the same. Okay? And you can also, if you don't like MPZ, you can use another loader here. For example, there are other libraries that allow you to do more than 2 parties, like MPSpeed is a library that allows you to do 3, 4, or as many parties as you want. There is also motion. So you see, just replace this box here, and then you get it. Yeah, like more MPC. Oh, you can also try to use some FHE with it. So basically, because this JSON arithmetic circuit is very, very generic. It just describes the circuit. So if you have some idea using FHE, you can also just write a loader in some FHE library and do it. As long as you support like enough gates, for example, if you have comparison gate. Oh, we have like some basic functionality as we described before. We are working on like with more improvements. For example, we would like to enable scaling, modular prime field arithmetic, some more like improvement on the description of the circuit, like for example, in the PPML, you can imagine that it doesn't have to be a multiplication, like between 2 secrets. If the coupler is the is the one who has the weights, right? So it is like you go from multiplication between two secrets to multiplication between one secret and one constant. You can do that if the gambler is the one who has the weight. And right, like it may be also convenient if you have arithmetic to Boolean conversion in this library. Oh, sorry. Yeah, we also have some wish lists, like those things. We don't think like we are working on them right now, but it would be nice to have input sanitization, some consistency check, active security, or some public auditability. Oh, and so I think that is the end of my talk. You can scan this link. It has like every link that I put before.
And now we have 5 minutes Q&A time. Does anybody have questions?
Thanks for the talk, Nam. I had a question around the trade-offs that individual applications can make for themselves rather than just throwing a generic MPC tool at it. So maybe for ML examples, right, wherein these are highly statistical and do not require like a lot of precision, can we maybe, what kind of trade-offs can we make? Can we make like the field size smaller and maybe that way it makes it faster? Or what sort of trade-offs do you see that individual applications can make for themselves?
Yeah, thanks. So the question is about trade-off.
Yes.
Try to make the MPC be more specific.
Yes.
So we can exploit something from it. So it will be less generic.
Right.
Yeah. So yeah, thanks for the question. So I put it here. So the reason why like I try to make this tool chain, this workflow so generic, because like there is no silver bullet. So maybe we want something, this, what I call the rainbow bullet. So you can change the back end. You can actually select what is best for you. For example, if you have a lot of linear operation, then it is best to use what we have here, MPZ, BMR16. That is like direct operation on arithmetic numbers. If you have a lot of non-linear, like you have a lot of comparison, or you have a lot of truncation, like bit shifting left and right, like you're doing AES, it's better if you use MPZ, that is in the Boolean format. Okay, so it's all about trading off what you think about your circuit is. You can also look at these new, like not so new. They're in the past, they are also not in Rust. So MP speed and motion, they have some of the protocols supported have let's say efficient conversion between arithmetic and Boolean. So not as efficient in arithmetic, not as efficient in Boolean, but if you have a mixture of them, this may be the backend that you want.
Do we have more questions? Okay, thank you, Nam.
Thanks.